So let's start. Good afternoon, all. Welcome to fifth week of discussion session of the course Finite Element and Element Method, course offered by NPTEL, and course instructors of this course is Professor Biswanath Banerjee and Professor Amit Shah. I am Asif Raza. I am your teaching assistant. Myself, I am a PhD scholar from Department of Civil Engineering, IC Bangalore. So today we'll be discussing questions relevant to assignment number 5. So let's start. If you guys have any doubt, please do ask in between. Okay. So first question is, what is the order of highest derivative present in weak form of Governing equation in Timoshenko beam theory? So uh, answers. Am I audible?
Hello, yes.
Yeah. So what do you guys think? What would be the answer? What is the order of highest derivative present in weak form of Governing equation in Timoshenko beam theory?
Timoshenko beam, the one is right.
Okay,
The
I'll write down the.
differential equations, governing differential equations consist of derivatives up to second order. So weak form for each equation consists of derivative for the derivative order one
Yeah.
or the first order.
Yes, yes. Answer is B. Okay, I'll try to explain how is it. So first of all, we need to know what is the Governing equation for Timoshenko beam theory. I'll just write dB. So it's d by dx of e by d theta of dx plus ksga correction factors and dw by dx minus theta equal to 0. This is the first part, and second part it's d by dx of ks ga dw by dx minus theta plus q equal to 0. So to find uh, yeah, this is my strong form. To find weak form, we multiply uh, suppose we multiply v1 with 1a and integrate, and v2 with 1b and integrate. Okay, so let's try to do this. So say v1 d by dx d by d theta dx plus ks ga dw by dx minus theta dx equal to 0. This is integrated from 0 to L. Then this using integration by parts, we'll have this one as v1 ai d theta by dx at the boundary 0 to L minus the v1 by dx ei d theta by dx integration dx 0 to L, and it will be plus v1 ks ga dw by dx uh, okay, and that is theta. So this can be integrated as in ksga w 0 to L minus 0 to L, this incremental type V1 V1 dx. If I write ksga here, then W and dx, and last V1 and ksga theta integration dx equal to 0. So this is a for weak form first part. So if you see in this equation, the derivative highest derivative is like what's the question asked is highest derivative present is, if you see first order, and here it will be also first order only. So seeing the first equation, its highest order is equal to 1, let's say 1b as well. So 1b 0 to L v2 d by dx of ksga d theta, sorry, d dw by dx minus theta plus q dx equal to 0 using integration by parts. We get first is this ksga dw by dx. This one is a whole. Okay, so this one at the limit. Now the next term 0 to L d v2 by dx, this one ksga dw by dx minus theta dx, this one, and the next term is 0 to L v2 q dx equal to 0. So this is my weak form for the second part. And if you see here also, the highest order is like, if you see this first term, it's a bounded term, so no worries. Here we have highest order is 1. So in this part is also highest order of derivative equal to 1. So my answer would be 1 only. So this is it. If I ask you like modify the question and ask you what will be the highest order of derivative in the governing equation, like as in strong form, what will be your answer?
Highest order for derivative of a governing equation is 2.
Yeah, you're right. So if question was like what is the order of highest derivative present in the strong form of Timoshenko beam theory, that is 2. Uh, and what is there in the Euler-Bernoulli beam theory?
It is 4.
Are you correct? Are you right?
In the strong form. 4 in the strong form and 2 in the weak form.
Yeah. Okay. Okay. Fine. Let's move on to the next question. So, question is, what kind of polynomial is used for interpolation of rotation and displacement in FEM of Timoshenko beam element? So I would ask you guys to type your answers in the chat box. Abdullah and Rafael has given their answer. What about Jace?
Uh,
Yeah, Abraham has also given the answer as B. Yes, the correct answer is B, Lagrange polynomial, as this has already been explained in the lecture series. So let's, if you guys don't have any questions regarding this, we'll move on to the next question. So moving on. So next question is, consider the following functional f of multivariable. Uh, it's a multivariable, and find the corresponding Euler-Lagrange equation. So my functional is dependent on x, y of x, y prime of x, z x, and z prime of x. So what will be my Euler-Lagrange equation pertaining to this functional? Yeah, Abdullah Rafael has given their answer as A. Just
Actually, this answer is very clearly explained in solution. So I believe
wait.
everyone in our company is absolutely clear with this question. But if any doubts,
Okay.
it should be okay.
Okay, I hope everyone is clear. Or maybe just a few things like if it had been only a univariate question, so you guys already knew what will be the solution. Like it will be like del f by del y d by dx of del f by del y prime equal to 0. So as is increases the multivariable, suppose this is yi, so you can increase it to del f by del y n minus d by dx of del f by del yi. Yeah,
I have a question about this
yeah, okay.
actually, but it is not regarding to our material in this week. But what if our governing variable as y? It's a function of two variables actually.
Okay, so you mean,
And
yeah, I got your question. You
okay,
are asking, what if my functional f is dependent on x, y, z of x comma y, like this, right?
yeah, like this. I believe that it's a typical question, yes, for variational
Yeah. No.
analysis. Oh, that's nice. If derivative is also presented, yes.
Yeah. So, okay. So in this, should I tell you step by step or directly? Your call. Okay, I'll just try to give a gist actually. When we are taking a variation, suppose, so in this our dependent variable is z. So we're taking variation with respect to z. So what we'll have is uh, del f by del z dz plus del f by del z prime dz. And uh, dz is what? Dou z by dou x dx. So in this we can write dou x dou z by dou y dx. So this, if I write this is prime, right? So this can be like with respect to x, with respect to y, and with respect to both x and y. So just keeping only these two. Okay. So dou f by dou zx plus dou f by dou zy. I think this step is clear for you all.
For me, it's clear.
Yeah. Okay. Mm, no. Uh, we just need to convert this to zx to zy in terms of z. Okay. So uh, mm, what is this? If I take with respect to z, it is zx. Uh, mm, zx plus mm,
Uh, I believe it should be just DZ,
no,
not
cause,
DZ with
cause
respect to.
I'm, let
I
me.
mean, I believe it should be full variation, not like partial variation with respect to x. I believe, but I might be wrong.
See, what will be the answer I recollect from my mind is this, del f by, it will be zx, and del or del y, del f or del zy equal to 0.
Okay,
Like earlier it was what? Del f by del z minus d by dx of del f by del z prime, if I was taking like that, right?
right.
Now, when it is a multivariate, the independent variable is multivariate, it goes like this. It's a partial differential, and with respect to that only. But in terms of second order, like if it is having del zx, right, del zy, in the next it will be like del f by del zxx, zyy, zxy. So there is a step involved in between, like it will be uh, a double derivative, single derivative like that, or mixed derivative. Let me see if I recollect that thing. How it was converted in terms of z only. Mm,
I believe dz variation of z in variation of z prime should be full, but this variation consists of variations in x and y, I
yeah,
believe. But in this form, we need
uh,
to write d as a variation of z. It will be partial z partial x dz plus partial z partial x dx plus partial no partial
no, you mean to
you,
say this one, is it?
yes, I believe this one.
I don't think this one is correct.
Okay.
Uh, I know for sure that the final thing comes out to be like this. I'm forgetting what is the intermediate step. Okay, let me check. Mm, mm. What if I do it in the last, like I'll try to recollect what was there in the mid,
Okay, of course, of course.
cause,
I believe
cause,
it's too difficult to
cause
answer at the moment.
I know for sure the answer is this thing, pertaining to what you asked earlier. Okay. So moving on to the next question. Uh, so in reduced order integration, the submatrix K22 can be written as follows. Identify the correct statement corresponding to the numerical integration to evaluate K22 and K22ij component is given by this equation. So the statements are: the first integration term is evaluated with full order, and second integration KSGFI is evaluated with reduced order. Second statement is first term is evaluated with reduced order, while the second is with full order. Third is both with full order, and fourth statement is both with reduced order. So what's the answer, you guys think? Am I audible to all?
Yes.
So do you guys know the answer?
I actually forgot the answer.
What about
But
yeah?
I previously in this week I asked that there will be a question about reduced integration
Mm,
method. So I have some unclear moments in derivation of this.
okay, okay. What about others? Answers? Any guesses?
But I can logically
Okay.
I try to think about it logically.
Jess has said option A. Abdullah tried saying option B, but not sure. Okay, I'll just give the answer. Answer is option A. So in this, what does it happen? Like there are two terms, right? 0 to L E I d phi I dx d phi j dx dx plus 0 to L kx z a phi I phi j dx. So if you see, this term is almost relevant to Euler-Bernoulli, but in order is a different thing, and this is like an additional term. This is cause of shear factor involved in this thing. So this term uh, this term is integrated fully, and this is having reduced integration. So this is full integration. And this is reduced integration. So in the week lecture, you guys have studied about that consistent interpolation method and Rayleigh-Ritz method. So this is what the question structure was telling about what is happening, what is about the order, and share locking and other stuff. Okay, so let's move on to the next question.
I have a question.
Yeah, sure.
Could you please briefly explain what problem can be solved by reduced integration? I just don't understand the idea. If we have this brilliant idea with consistent interpolation, why we need to use reduced interpolation at all? This is this step. I don't understand why we need this.
Okay, see, FEM is all about approximate solution. We don't have an exact solution. We are trying to get to the as close as possible to the exact solution, but not the exact solution. Uh, so, reduced integration and full integration sacrifices in terms of integration points. Like, suppose uh, if an uh, order of polynomial, oh sorry, uh, suppose degree of a polynomial is 3. Okay, degree of a polynomial is 3, and I take an method where uh, order of integration it takes, it's like full, at full it gives 3, reduced it gives like 1. Okay, so when I take the full, it gives me an exact solution, and in reduced it does not give me an exact solution, but what it does, it give me a solution which is little bit closer to the exact solution. It's all on the choice of uh, the person, like what does he, how much accuracy and precision he wants to. Okay, am I audible? Abdullah is written, I'm not able to hear.
For me, you were audible because I believe it's a connection issue.
Okay, okay. That's why he left. I think he will again connect. Okay, I'll try once more. See, in the full integration, suppose the degree of polynomial is 3. We take 3, it will solve for all the polynomials. It will solve for all the polynomials having degree 3 to 1. In reduced integration, it will give me an exact solution for 1, but it won't give me an exact solution for 2 and 3. But it could be that our choice of accuracy and precision required is that the answer given by the reduced integration is sufficient for us. See, FEM is all about computation, how computation costs. So, if we increase the number of integration points, the computation cost will be correspondingly very high. I mean to say, uh, suppose in first order of integration, in first order, is there any connection issue for you all?
Everything is okay for me.
Because two of them actually left and again rejoined. Yes, for me, I don't know what's the issue. I'll continue. If you guys don't understand, please ping me. I'll try to again explain. I'll try. So, suppose first order of integration, it takes only one integration points. Okay. In second order of integration, it takes two integration points. This is in only 1D I'm talking about. Like if I want 1D in the sense like my independent variable is only x, suppose x. Uh, so only using one integration points, like okay, is y equal to f of x, right? F of x is there, is x, x1, x2. This is f of x. We just take a one integration point for first order of integration, and we just get this area done. Okay, in two integration points we have in for two integration points, suppose we are having this 1 2. This is just in terms of 1D, and this is only in one element I'm talking about. So you can imagine that we take a large number of elements for solving a complex problems, plus it could be 2D 3D, so it gets multiplied. Like if it had been a 2D problem, it will be one by one only, but for this, like if it's a second order and 2D problem, it will get into 2 by 2, so number of integration points get into 4. It's if it is a 3D, again it gets multiplied and it become quite cumbersome. And you're seeing that this is just only for one element, So if we keep on taking, if I keep on increasing in number of elements, the number of integration points will be innumerable, like it will be very high. So to sacrifice our calculation perspective, in the sense accuracy and precision, how much we want to take into account, so we get on with this reduced integration. Plus one more additional feature of this reduced integration is, one more feature of reduced integration is this. Say suppose a cantilever beam, we apply a load, so it deforms like this. Say what an FEM solution gives, it's like, or maybe like this, if I'm taking suppose. So FEM solution gives a stiff solution. FEM solutions are
Okay, I
stiff,
got your point.
stiffer than exact solution. So to smoothen, like to reduce that stiffness, we, if we take into account of this reduced integration, this will give a smoothing feature. So one additional advantage of reduced integration is that thing. I think this thing is just the just, you will get into more detail maybe later on when he will explain about that numerical quadrature, Gauss quadrature. He will taught you in the subsequent lectures. Okay, moving on to the next question.
Yeah, thank you.
So in Timoshenko beam theory, primary variables are W and theta. Uh, if we use linear interpolation for both the variables, what will happen for thin beam? So what do you guys think? What is the answer?
Shear working.
Okay, contribution from bending energy will become zero and shear locking will happen. So yeah, most of them has given an answer as option D. Yeah, you guys are all correct. Answer is shear locking only. Option D is contribution from bending energy will become zero and shear locking will happen. So I think you guys all already know this. We'll move on to the next question. Question number 6. Identify the correct statement regarding consistent interpolation in Timoshenko beam element. Option A is displacement and rotation both are interpolated with same degree polynomial. Option B, displacement with n plus 1 order while slope is interpolated with polynomial of order n. And option C, it's a vice versa thing. And option D, none of this. Okay. Rafael and Abdullah has given an answer. Option B. Others. Yeah, Rafael, you want
I
to
remember
say?
your question about this. Uh,
Yeah,
a lecturer said several times about thin beam,
yeah,
and he was discussed this. Was discussing this with respect to uh, reduced integration also.
yes,
But in Timoshenko bars, we don't have that. Wow, our dy, our dv, our displacement derivative is equal to d theta. But why we need to do it with respect to uh, thin beam? That we
yeah.
need dw dx there.
Okay,
Could you
so
please clarify thin beam with mathematical point of view? Why we need this derivative?
okay, so uh, okay, I'll just say one thing. We solve a bar problem sometime, right? We consider it as a 1D, but in reality it's a 3D, right? But the dimensions of like uh, breadth and height are very much less than the length. So we consider it as a 1D object and solve our problem. Uh, in thin beam theory, shear why there is a difference of different like Timoshenko beam theory and Euler-Bernoulli beam theory. You should understand the difference is that in Timoshenko and Euler-Bernoulli there is a difference of shear into play. Like in Euler-Bernoulli, uh, shear stresses does not come into play into that much, but in Timoshenko shear forces come into play. Normally Euler-Bernoulli is more closer towards thin beam or towards 1D kind of thing. But if thick beams are used, shear forces or shear stresses effects are larger. So we can't neglect those things. So shear will have a dominating feature in this. We can't neglect the feature of shear stresses. Uh, in thin beam, shear first of all, as we just studied this one, uh, this is like the shear part. This is more towards the bending part, right? So this had a full integration, this had a reduced integration. Shear part had a reduced integration scheme used. Now uh, so if thick beams are used, if thick beams are into play, shear stresses effects are larger. So if we are using reduced integration, that is not giving me conclusive or apparent effective results because shear stresses effects are larger, and we were using reduced integration for shear term. So that is like more effective for like thin beams only. For thick beams, we need to effectively utilize that shear term as well. I think I hope this gives you an idea. Yeah, Rafael.
I'm asking about. I understand what you're saying. This is how to say that it is a common thing that we can meet in first course of strength of material. But I'm interested in the question. Look, earlier Bernoulli theme. The plane sections remain same.
Uh,
It means that actually W dx is equal to
equal to theta.
equal to theta. This means that in Euler Bernoulli, all beams are thin with this
Yeah.
with this. It means actually this. So in Timoshenko beam, we introduce new variable theta, and it is not equal to dw dx. But why we need to describe thin beams with Timoshenko theory? I believe all if it doesn't work, why we need to be patient about that? Or be interested about that? Why we introduce a variable that depends
So
on something, and after that we again try to fit our Timoshenko beam to the dw dx is equal to theta. I don't understand this thing.
okay. So see, Euler-Bernoulli is applicable for when dw by dx is equal to theta. So here shear forces are not into play that much, and this is applicable when the beams are very thin, and Timoshenko beam theories are very much applicable for thick beam. But there is a transition feature is also going on from thick to thin, right? So we can't absolutely define a line that you use Euler-Bernoulli here, you use Timoshenko here. There is a transition feature is also there. So there a reduced integration scheme we are using, which is known as consistent interpolation scheme. I hope that does make sense. Yeah, Rafael.
Sorry, I have a last question about this. I promise. Uh, when the first lecture introduces with the hint that describing shear deformation and writing shear deformations in terms of dw dx, we end up with shear stresses in beam in earlier Bernoulli in earlier beams. We end up with zero shear
Shear stresses.
zero shear strains, and we conclude that there will be also zero stresses. But why we in common strength of material courses, why we consider Juravsky formula for shear stresses? Like, this um, from this is no, you know this formula. I believe we can conclude that in the center of the section there will be maximum shear stresses, and when we have a free surface, shear stresses will be equal to zero.
Zero.
I believe the strength of material allow us to consider Euler-Bernoulli beams with shear stresses in them. But I don't understand how
No, but
theory of yeah, yes.
in Euler-Bernoulli beam theory, we consider most of them like effect of bending. We don't consider the effect of shear stress, taking it as a only 1D thing. Suppose this section, if you see the cross section, we see the effect of only bending in each section. We are not considering the effect of shear stress or strain. Uh, that's where it is making a difference, I would say.
Juravsky formula is not. It means that Juravsky formula is not consistent with
I
the.
am not recollecting what formula you're saying.
I believe you know this. The dependence of the shear stresses along the section. I believe you know this. Can I
Yeah. What?
can I share my screen? You will see my this
Yeah, yeah.
formula.
Please share it. I am not getting what you are trying to ask though.
This is in Russian, sorry, but I believe you know this formula and this one.
Share it. It's not okay. First of all, I'll stop sharing mine. No, please share it.
This one.
Okay. Yeah. The name
I
which
believe you know
you
this formula.
yeah, I do know that formula, but the name which you were saying, it was quite new for me.
Okay. I actually decided to call it in this way because I also see that in from Reggie's book he uses this surname, the last name of Russian scientists. I
Okay, okay.
thought that there's also familiar. You are also familiar with it, but it doesn't matter actually.
Yeah. So don't get too much into that thing. I would say. See. Okay. Uh, to get the functional for Euler-Bernoulli, what do we consider? Uh, this is what we had. Like, uh, for the Euler-Bernoulli scheme, but for uh, uh, Timoshenko beam theory, we had an additional term. This is what I'm telling you. Like uh, for Euler-Bernoulli, only bending is into effect, while in Timoshenko beam theory, there is an additional feature: shear is more protruding. Like it's not becoming zero as you saw earlier. Like d theta, sorry, dw by dx is not equal to theta for Timoshenko beam theory.
But you know this K coefficient. You
See,
know this K coefficient.
one more thing is Timoshenko beam theory is a more general theory as compared to Euler-Bernoulli. So there might be a case where dw by dx
Is equal to
might become equal to theta. So that
yes, yes,
is that is directly will give me an Euler-Bernoulli theory, right?
right.
Beam theory. So
But
yeah,
this K coefficient, I want to say that there we introduce K coefficient
cake.
in Timoshenko beam K. It is in our weak form. It is a KGA. You know, it's
Oh,
about
okay, okay.
this K. We introduced this K. I tried to Google about this coefficient, and a lecturer also said that in our Timoshenko beam, shear stress along the section is constant. But after that, he referred to this formula, Juravsky formula, that I don't know how you call it.
Actually, why he is using K as cause of this cross section only. Cause cross section is not same all throughout for this Timoshenko. It will change, right, as we deform.
Okay.
So taking into that effect, he introduced this KS. So because we are using area A, GA.
Have you calculated? Have you have experience in solving Timoshenko beams governing equations?
Uh,
Like we did it in Euler-Bernoulli. If we have some forces, simple situation. Have you calculated Timoshenko
okay, so you
beams?
want me to what solve this strong get the governing differential equation
No,
for
no, no. I just asking you. Have you solved these equations by hands or by some numerical stuff or not? I wanted to. I want to ask about the details of that. If you don't solve, we just move forward.
I just get it like as an overview. I don't get into much that I would say.
Okay. I'm just wanted to ask about the details of that with respect to our standard Euler-Bernoulli.
Okay.
For me, it's strange that strength of material uses Euler-Bernoulli with stress distribution along the shear stress distributions along the section. We did it all the time in strength of material courses, but lecture of finite element method begins with the step that says, you know what, guys? Actually, there's no shear stresses in classical Euler-Bernoulli. It's like it's very surprising thing for me. And he proved that this is not the case for Euler-Bernoulli.
Yeah.
I just wonder how we used that, and it was consistent. We use that all the time. We use Euler-Bernoulli and shear distribution along the section. And for me, it's very strange. Therefore, I decided to ask about this.
Uh, Actually, that's why I said when the cross section effects are more into play, when the cross sections effects are more into play, then only shear stresses is more likely to happen. Otherwise, I don't think. Because shear stresses what it happen like one layer slips over another, then only shear stresses develops, right? So if the cross sections are like big and it's sliding layer by layer, then the shear stresses will have an effect. That's what I feel. Anyway, I'll move on. I'll just give the gist of this question. This was like question was what is the correct statement regarding consistent interpolation in Timoshenko beam element, and most of them given an answer as option B. So displacement is interpolated with n plus 1 order polynomial and slope is interpolated with polynomial of order n. So what it happens in consistent interpolation is we keep dw by dx and theta order to be same. So so naturally the displacement order would be n plus 1 if theta order is n. Okay, so moving on to the next question. Yeah, so this is more towards what will be the functional of this Timoshenko beam theory. So question is, a cantilever column is subjected to axial load P naught only if its total potential energy is written by this is due to the bending, this is due to the shear, and this is due to the axial force, where Wx is the transverse deflection and theta x is the rotation. What will be the corresponding governing equations of the beam? Consider W, theta as primary variables and consider psi is equal to this. Yeah, Rafael?
I wanted to add a question to this question. I believe we just if I believe for this question we need to go into details. Like we need to differentiate with to no, we need to write our earlier equation and end up with governing equation after this. But I want to ask you about the situation. What situation in this case? Could you please um, draw a situation where our potential energy will have this form? I mean, everything is clear, but it's not clear how we derive P0 term here. What is going on there? It is some sort of elongation here, or what? P0 term is not clear. How we need to apply this force for our beam in order to have this term in potential energy?
Okay.
I believe it's like axial elongation here.
Yeah. Okay. So you guys know these terms. You are confident in this aspect. As suppose you just need this term, right? Third term, considering this P naught.
This is my question. I don't know about other kinds.
Okay. So this suppose this is the earlier problem. Question is we are applying a P naught and it deflects. Suppose. And P naught is still in this direction. Okay. Okay.
Okay, it means that we need just include in our potential energy elongation term.
Yeah. Think what. So we have to include the painting dw by dx p naught by 2.
It's clear then, because potential energy for stress elongation is epsilon xx multiplied by stress by p0. So I believe it will be clear.
Yeah. So do I then again explain or not explain?
My question, I don't know if everyone is interested in that. I just understand that this is elongation term. If this statement of the problem say nothing about this, so I try to adapt this equation to real situation. And real situation is it is elongation term, and then it is interesting for me because we are not considering elongation with with beam
Yeah, so
classically.
yeah, yes. We directly don't take into effect. We have this independent variable or primary variables w and theta, and we have x. We use x. So indirectly we compute how much elongation it happens in the x direction. So in Euler-Bernoulli beam theory also, like when you take m by I sigma by y, there also uh, uh, you take sigma xx epsilon xx. There is a straining in the along the x, right? Sigma yy. uh, I hope it makes sense.
It makes sense, yes.
So okay, moving on to the question. Question is, we are given with the potential. We need to get the governing equations of the beam, and I suppose are they related to boundary condition now. Okay, so let's move, solve it, uh, leave it. Okay, so our functional is I ei by 2 0 to 1 or L, sorry, 0 to L d theta by dx square dx plus ksga by 2 0 to L dw by dx minus theta square dx minus p naught by 2 0 to L dw by dx square dx. Okay. All right. So earlier so this pi is having functional dependence on x, theta of x, w of x, theta prime of x, w prime of x, right? So for this, earlier uh, we had two functionals, right? So with respect to theta, what will have del by del pi of del theta minus del d by dx of del pi by del theta prime equal to 0, and second will be del of del w, right? This is like only first variation. So del pi of del w minus d by dx of dou pi by del w prime equal to 0. Here theta prime is d theta by dx and w prime is dw by dx. I hope that makes sense. Okay, so this one would be what? So dou pi of dou theta. Theta we have only here. Theta we have only here. So when we take the derivative with respect to theta, we'll have ksga by 2. That will be dw by dx minus theta times 2 and minus 1. Okay, and this is theta minus d by dx of dou pi of dou theta prime. Theta prime is here only. So this will give me ei by 2. It will be 2 theta prime and theta double prime. No. 2 theta prime only.
Sorry, why you put minus here?
It's this one. Are you asking here?
No. This is correct. Uh, you are minusing the minus dp the theta. Dp the theta was positive, and
No.
you just,
You're saying here, right? This one.
no, you add minus. This is the next step. You just differentiate that with respect to x, or what are you doing
No,
at
it's
the,
just
at the
this
bottom?
statement only I'm writing. The first term is this one. First term is this one. Second
Okay.
term.
Why you subtracting this term?
No,
Why you subtracting? Or
uh,
you
I'm writing the Euler-Lagrange equation, right? This is how we get into, like, when we take
you
the.
you multiplied this equation by minus one, yes?
Hmm? No, I haven't multiplied yet.
But we have the bottom line. What does it mean? Bottom line is dp d theta or what? D pi
Uh,
d theta.
okay. mm, This one is actually dou pi of dou theta prime equal to.
Okay. Oh, d theta. Okay. Yes.
So the that is equal to what? Ei by 2 2 theta prime, right? See, theta prime is here only. So Ei by 2, this is theta prime square, so that will give me 2 theta prime.
Sorry. Look. dp d theta. Where it is? dp d theta prime. D theta prime.
Okay, you're confused here. Theta prime is d theta by dx. I mentioned it here. Okay, let me rewrite this pi in terms of prime. Then you guys
The,
get
what's
it.
what was the first step? I'm sorry.
0
What
to
was
L.
the first step?
Okay, let me write it more simplified way. Theta prime
So,
square dx.
dear sir, this was absolutely clear. I'm not confusing in this.
Okay,
D theta, yeah, I know what is d theta prime is. For the first term. What was the first term? dp d theta.
d
Yes.
dou pi upon dou theta prime. Acha, okay, you're asking this. This was dou pi by dou theta.
Oh, okay. I thought that you started with the second term. Sorry.
Ah,
Sorry. Everything is clear now.
okay. Okay, I hope others are also not having issues. Maybe clear. Okay, move on. So, solving this will have KSGA. 2 gets multiplied. We have minus here, so minus when gets multiplied, it will give me theta minus dw by dx minus d by dx of ei theta prime equal to 0. This will imply, if I write it as d by dx of ei d theta by dx plus ksga dw by dx minus theta equal to 0. Okay, think, yeah. So this is my first. Second one is del w of pi. So that is like del pi by del w minus del d by dx of del pi by del w prime equal to 0. This is dou pi by del w is, we don't have this term, the blue term, so that is 0 minus d by dx of w prime is here and here, so this will be ksga twice of dw by dx minus theta, right, and that is it there, plus this is minus actually, minus p naught by 2 times 2 dw by dx. Okay, this is a complete equal to 0. So this implies d by dx of ksga to ksga dw by dx minus theta, and this is, and that is plus p naught d square w by dx square, considering p naught is constant. If p naught is a function of x, then d by dx will be outside. Okay, so this is, we have as a second, psi was equal to what, ksga dw by dx minus theta. Psi was ksga,
Sir,
yeah,
do we need to keep two term? You have two ks. I believe it divided by two both terms. We need not to keep two in the first.
okay, then here we need to make it p naught by 2, right? Oh, okay, I made a mistake here. Okay, the here does not need to be 2, ksga by, it was here 2, yeah, sorry, thanks, ksga. So now the Euler-Lagrange equations can be modified and written as d by dx of ei d theta by dx plus, this is ksga dw by dx minus theta, which is psi equal to 0. This is part 1. Part 2 is d by dx, this is k, this is psi plus p naught d square w by dx square. Okay, so these are the answers. So let's see. D plus psi. So with that, it's this thing, and we have plus minus. This is coming as a plus here. Did I make any mistake? Okay. Here it was minus outside, so this will be minus only, minus. So the correct answer would be this one. Hope that is okay with all.
For me, it's okay.
Abraham, I hope you don't have any doubt now. Others? If you don't ask, I will think you're okay. Okay, moving on to the next question. So it's a long question. Okay, before this, I'll ask this simple question. So, what is major difference between Timoshenko beam theory and the Euler-Bernoulli beam theory? So the options are: plane section is no more plane during bending. Second option is plane section orthogonal to neutral axis is no more orthogonal. And third option is strain energy density contains major contribution from shear deformation. Option D. Both option B and C are true. So what do you guys think? What is the answer?
We discussed this thing with students. Uh, Actually, my first option was A, but I then decided to shift to D. But you know what? What here means the word major. It means that we have a major contribution from shear than from deflection, or what?
Yeah.
If it is the case, it is wrong because deflection still comparable with shares. I believe that this was not correct. For my first option was A because I don't understand why we use major. Major contribution means it is greater than deflection energy, or what?
Oh, okay. There it's creating a confusion. I think I hope that the statement talks about like in Euler-Bernoulli, uh, uh, there is no contribution from shear deformation. I would say, but in Timoshenko beam theory, there is a lot emphasis on this shear deformation. That's why uh, uh, it's making. Distinguish between Timoshenko and Haller Bernoulli. Like, what is the major contribution? If we see compare Timoshenko and Haller Bernoulli, what will be the major contribution? What is the major distinction between those two? Is the shear deformation plays a quite an important role.
Okay, major contribution now is clear.
Okay.
Major, major, we need to understand major contribution with respect to Euler Bernoulli beam
Ah,
theory.
yeah, yeah. Okay, so that option D is my correct answer. Okay, uh, let's do
By
the
the way, interesting thing about the previous question.
yeah.
Uh, A plane section. Could you please again show that? Plane section is no more plane during the bending. Today we are already just discussed that in beam in Timoshenko beam we actually can obtain that our plane section will remain same at some point. So Timoshenko beam allow us to uh, have plane sections also. So
Yes, yes.
one interesting question that Euler Bernoulli can be included in Timoshenko.
So in that way, Timoshenko is more general, right?
Yes, yes.
Yeah. Uh, if we don't consider plane section no more plane during bending, then uh, there's a step ahead of this Timoshenko as well, considering more it as a more general 3D thing, I would say. Okay, let's solve this question first. Identify the incorrect statement corresponding to Timoshenko beam element. So, better observe this. This is regarding a beam element of Timoshenko beam theory. So, option A is two node linear element with reduced order integration can capture the thin beam response, but number of meshes required is high. Option B, two-node linear element with reduced order integration cannot capture thin beam response. Even higher number of mesh as it considers linear variation of displacement, whereas the actual deflection is cubic or higher order. Option C, it's reduced order integration with quadratic element perform better than reduced order linear element for thick beam. And option D, in Timoshenko beam element, reduced integration element performs better than full integration element. Uh, Rafael, I can still see your screen shared. So, what's the option answer? Any guesses?
Incorrect statement. The
Yeah, yeah.
interesting here. Actually, a two-node linear element with reduced order integration can capture. So the lecture was devoted to this. Well, the last lectures was devoted to that. To this. So B is wrong, I believe. So the main reason of reduced step integration lecture was about, what, guys. Actually, reduced order integration can capture all stuff with respect to Timoshenko beam. And you already point to us that it is about a calculation costs question, not about
Computation cost.
computational data.
Yeah,
Computational costs.
as I told you, when I say reduced integration, I told you full integration scheme. Okay, so if our problem requires is degree 3 and full integration scheme gives me 3 and reduced integration gives me 1, so it won't give me an exact uh, result, but it will still give me a result closer to the approximate. It will give me an approximate solution, but it depends how much accuracy we want, or we are satisfied with it or not. But if our problem statement is suppose degree 1, full integration will also give me an exact solution, reduced integration will also give me an exact solution. So this is where you need to see what kind of problem you are dealing with. I suppose that makes sense. There actually I put emphasis on the computation cost because uh, that's where actually people deal with, like when you refine the meshes also, as you have already seen that when you increase the number of elements, our uh, answer closer to the exact solution becomes more closer and closer as we refine the number of elements, and that is what mesh convergence is all about. But we need to balance, like at how much refinement we can deal with. Like as we increase the number of elements, our time taken for that solution becomes very large, and that is what computation cost is all about.
I believe question here is important because you know what? Sometimes if we have a wrong understanding of phenomena and we give to this some integrate some finite element method, we creating weak form. We did all steps regarding to our integration, but why it is important here, I believe, because reduced integration scheme actually can be used in our Timoshenko beam theory. This is important. So it captures phenomena
See,
that
I would just say full integration and reduced integration scheme is all about solving how are you solving integration. Uh, uh, to get the stiffness matrix of a particular element, we integrate it over the domain from x1 to x2, right? So how are we integrating that domain? That is where integration scheme, that is what integration scheme is all about.
so initially we say in lecture that actually if we use the same order of interpolation, it doesn't work. We say this, so it not captures the phenomenon. If we use the same order with interpolation, it will not work. But
Uh,
with combining reduced integration scheme and using the same order of interpolation, it actually works.
Okay,
So,
okay.
as
Uh,
I understood here, reduced integration scheme allow us to use the same order of interpolation, which is actually a trash to use here because we understand that displacement is a
no, 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 no.
have
Let me check. I don't. First, ask me this. Let me ask this question. You said
okay.
in the reduced integration, you're saying order of interpolation is same with full integration. Do you mean that thing?
No, no. A reduced integration scheme use interpolation of the same order. As I understood this, we will use interpolation or the same order for displacement and for shear, for angle. Sorry, for theta,
Slope and slope and
slope and deflection. Yes.
yeah,
So
slope
we,
and
we u- as I understood, in reduced integration scheme, we will use the same interpolation. But earlier in the lecture two, we was clearly stated that this is not okay because we will have shear locking phenomena. And after that, using reduced interpolation scheme, become to we have a success because it actually works in the capture phenomena. This is how I understood that.
so this is what uh, like this is a problem actually when you use an over stiff mat like over stiff element that I told you like FEM approximates all the solution in a more stiffer way, and that could generate spurious modes or the shear locking phenomena as it was said in the lecture. There are other two more prominent problems with FEM are like hourglassing and volumetric uh, uh, don't remember. So still it's not like FEM is a dominant thing. So people get by with this nowadays. What people are doing is they don't normally solve this by displacement based scheme. They try to use mixed FEM methods to solve this volumetric or this shear locking feature. To get by with this shear locking feature, nowadays people are using mixed finite element method. That is a quite complex thing. I'm just giving you a gist. So it is not that when if you are using a full integration scheme, my answers are completely correct because FEM is all about taking an approximate function like our functional itself. Like we are taking a trial functions, right? Those are actually an approximation, n1 n2 or xi1 xi2 are approximation. That doesn't necessarily mean our answer is correct.
I understand that this is approximation, but
So
I understand this.
if we are approximating something, if we are making something easier, there would be some repercussions pertaining to it that we need to deal with.
Okay.
Yeah. Okay, so the correct answer is option B, two node linear element with reduced integration. Correct answer is option B, which is the incorrect statement corresponding to Timoshenko beam element, which is two node linear element with reduced order integration cannot capture thin beam response even higher number of mesh as it considers linear variation of displacement, whereas the actual deflection is cubic or higher order. Okay, so let's move on to the next question.
Excuse me.
Uh, yeah, Abdullah.
Yes, actually, I want to ask about if you are familiar with Abacus software when you are using when you are choosing the element type
Uh,
for a
uh,
cubic.
Excuse me. Sorry, but your voice is somewhat. echoing.
Is it now clear?
No, it's still.
Noisy. Just 1 minute. Now?
No, it's better.
Yeah. Actually, if you are familiar with Abacus, when we are choosing the element types, especially when it's cubic element type 3 node, so it's C3D8R, and R is referred to reduce integration.
Yes,
Does
yes.
it have relation with this?
Uh, Actually, I don't have a hands-on experience with
I
Abacus.
believe yes. I believe yes. We can use polynomial of degree 3 with reduced integration scheme. It is about integration, not about how much you what is the order of a polynomial. I believe this is clearly it refers to this.
Because, yeah, because it's the same polynomial, but just the reduced integration.
Yes, we in the stiffness matrix, I believe we will use this. We reduce integration for each term, not a fully integration thing. That reduce computational cost will be less for this, but we can use approximate. We can use approximation for each term. Uh,
See,
I believe
again,
this refers to
uh,
this.
yeah, I beg to interrupt. Sorry to interrupt. I'd say that still I'm saying this integration scheme is all about how we are integrating our stiffness matrix, how we are getting that stiffness matrix. Like for every stiffness matrix, uh, KEL, we are integrating from x1 to x2 some EI d phi I dx d phi z dx, right? This is we are trying to get, and for this numerical scheme we use is quadrature or integration rule, where uh, 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 the order of integration could be different as to what you are taking for that element itself. I would like to iterate by saying, suppose our element is a linear element, but our integration scheme could be 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 by 3 could be quadratic order 2. Uh, I hope this is what I was trying to say. I don't know if you guys mean this one or
Yes, we're talking about this.
yeah.
So I believe Abdullah also say about this. We are talking about Gauss integration,
Yeah.
and if we are using approximation with for order 3, we can use a Gauss approximation. I don't know. We can choose this Gauss integration, and we can use a reduced integration method
Yes.
for that. I believe.
Yes.
Actually, your colleagues in NPTEL, the course is called Finite Element Methods from Variational Scheme to Code. Your colleagues they choose a method that for all schemes we will use Gauss integration, and therefore from that course we can easily see that sometimes with Gauss integration we will obtain the correct, sorry, not correct, exact integration, and for some points we will use reduce integration. I believe it refers to
Yes.
that.
Yes. 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 I hope Abdullah is also clear in this regard.
Abdullah, if you not understand, Gauss integration schemes was a subject of the next lectures.
If you guys are not clear in the subsequent lectures, the Gauss integration scheme will come into play. So you don't have to look much into this. Okay.
Abdullah, I just
Share correct.
up to now we will integrate all terms of stiffness matrix by hand, but we can do this in a numerical way.
Yes.
And of course, we have not exact integration of each term, but Gauss integration creates a scheme. It is a unique scheme for all scenarios. We just use points and do integration with usage of that point. We don't actually integrate.
Okay. Okay, let me try to explain what is Gauss integration is. It I told in the earlier discussion. See, suppose this is fx. Okay, this is x1, this is x2. We want to find fx dx from x1 to x2. This is what I want to find. Okay, so rather than doing the actual integration, okay, so rather than doing the actual integration, uh, we want to use an integration point itself and just find the value of that function at those points and simply add it rather than integrating do the actual integration. So suppose if it is a 2-point integration points, say x1 star, x2 star. Okay, so we find uh, value at x1 star and f x2 star, and there is a weight attached to it at x1 star and x2 star. So we will multiply the value at those points and just add this thing. This will give me an exact solution. So uh, suppose say my fx is a
Sorry, sir. You said this gives an exact solution. It's not always
good.
give exact solution.
Yeah, it won't give an always an exact solution. Some degree of polynomial can give an
Some
exact,
degree, yes, some degree. It's a crucial point.
yeah, some degree can give an exact solution while other might give an approximate solution. So let's say our question which we want to integrate is having a form ax plus b, which is like degree 1, right? So if I use a Gauss integration point of 1, say, so with that my I will be what? W1 fx1, because I'm only using only one integration point. So that will imply what? I is, if I solve ax plus b x1 to x2, the exact integration of this scheme is what? Ax square by 2, which is a x2 x1 square by 2 plus b x2 minus x1, right? Okay, now our integration scheme is I is giving me w1 f of x1, that is w1 uh, okay f of xp, I would say. So that will be equal to a xp plus b, that is equal to a w1 xp b w1. Okay, and 1 and 2 are equal, right? So a 1 and 2 are equal. Suppose if 1 and 2 are equal, that will give me what? W is equal to x2 minus x1 if you consider coefficient of b, and coefficient of a will give me w1 xp equal to x2 square minus x1 square by 2, and as from this part w1 is equal to x2 minus x1, this is equal to x2 minus x1 xp, this is x2 minus x1 and x2 plus x1 by 2, So this will give me xp is equal to x1 plus x2 by 2. Okay, so what is this saying is we had this function, right? So suppose when we are having a linear fx, right, x1 x2, we select xp which is equal to x1 plus x2 by 2. So this f of xp multiplied with x2 minus x1 will give me an exact area of this domain. I hope this makes sense.
Yeah, I found a lecture from course of numerical integration from NPTEL. There will be a detail about that for
Okay,
polynomials. I believe it will be useful for Abdullah.
okay, yeah. I hope because I solved for linear first order.
Yeah, yeah,
You
yeah.
guys can
Yeah,
go through for further higher order stuff. Uh, I wish to end the lecture here because I have some work to do today. Uh, I think this is already in the assignment or solution provided. So uh, I hope you guys don't have any doubt. If you guys have any doubt pertaining to question number 8 and 9, please ask. Yeah, Rafael.
actually, last time we have some. We discussed that we will discuss some points here. The first point
Yeah.
is no, the p is here is between the element. Do you
Yes.
see?
Yes. Yes.
But as we need to have a p only in the nodes.
No, but see, what we are having is a Timoshenko beam element, and in
Actually, reduced integration technique.
oh, okay,
It means that
that's
we consist also two nodes.
okay. So then we need to just convert this p into p by 2 to end nodes. Like this, p will be transferred to this node as p by 2, p by 2. If we
Why we
are,
can do that?
huh? Yeah.
Why we can do that?
Uh, no. It's all plus some moment will be also there. Okay, how should I do this? Mm, okay, so the integration scheme which we use is what suppose uh, it was phi I ui. I suppose it was kind of this. Okay, so when we multiply, because this is a load thing, to get the nodal loads fi, what do? We multiply f phi I with q and integrate it with within the domain x1 to x2. This is what we do, right?
Yes.
Yes. So when we will do this, we have p here and n1 n2 or phi 1 phi 2 and q multiplied dx. So 0 to or x1, I'll just write x1 x1 x2. So that this scheme will only convert this f as p by 2 p by 2.
That's actually not so much clear.
Okay, okay, let me say 1 minus x upon L, and this is x by L, right? Uh, P
Yes.
dx integration 0 to L, if I take it like this. So what will have? First term is 1 by xl times p.
Sorry. Can I ask here
Yeah,
why
yeah.
you choose P for uh, for the force that is applied in the point?
Okay.
We can we use that? Okay. Okay. I actually didn't do that with Dirac delta.
This is what L by 2, right? I also forgot I got this. So when you integrate this, see, this will be this thing. Okay, p is 2 times. Okay, now it's fine. See, so what is direct delta scheme? I hope you guys know. Like when we have this scheme x minus, or just write f x throughout the domain minus infinity to infinity dx, this is what f of a only, right? So
Yes,
this,
right.
so this would be equal to, this f vector would be equal to p, uh, 1 minus l by 2 of l, and p l by 2 divided by l, right? L by 2, sorry, l by 2, because I'm replacing x with l by 2. I hope you guys don't have any issues.
Yes, yes.
So now this will just will have what, p by 2, p by 2.
Okay,
I
it's clear now.
Yeah. So I don't. I hope you guys don't have
Question
any other doubt.
for reduced integration scheme.
Yeah.
Should you one moment of lecture was unclear, but you say that we will discuss today, but it's not like fast question. We need to discuss this at some time. I don't know when.
Okay.
This is
So
you need to finish right now, but it is not like fast question.
okay. Okay.
We
So
need
can we do it sometime later? Cause I have some urgent
okay.
work to do today.
We need to do it in we you mean we will do it in
In the
connection
next
session
session.
or
Next session.
or
Next week, Saturday itself. I hope.
okay, let's try.
Okay. Uh, so I'm ending the session today here, if you guys don't mind.
Yeah, no, no mind. But I just want to ask if the previous sessions will be uploaded or not.
Yeah, previous sessions are uploaded and I think shared. Okay, if you guys don't have the link, I'll just give you. I'll just write it here only. Just give me a minute.
I can give a link to upload.
I'll just, no worries, I'll just paste it. So this is the link for the first lecture, and you'll go through this. Uh, I think you'll get all the. Okay,
Abdullah,
okay.
this is a link where there all sessions
Uh-huh.
are
Got it,
collected.
got it. Thank you very much, both of
Oh,
you.
yeah. Okay. Ending the session now. I've done.
Have a nice day. Thanks.
Yeah. Yeah.
Have a nice day and thank you. And
Yeah.
is there on Monday anything?
No, no, no. I don't think so.
Okay, thank you.
Okay. Bye. Have a nice day. Have a nice
Have a nice
weekend.
day.
Yeah. Bye. Bye, everyone.